In example 2 through 6, we are going to work on some engineering applications of partial derivatives. Why don't we start with this example number 2 right here. In this example, we have 3 resistors connected in parallel. So the first thing we know about them, they are connected in parallel. And we also know that the first resistor is rated 30 ohms, second one 45 ohms, and the last one is rated 90 ohms. And then they want to know how much will a change in R2. So we are talking about R2 in specific here, how it's going to affect the overall circuit resistance. What does that mean, overall circuit resistance? It means the total resistance of the whole circuit when all the components and all the resistors are combined. So we are going to use this different variable to represent that, R total. And that's going to be for the total resistance of this whole circuit. Now the next thing I'm going to do here is to translate the question that they give to us right here into something that is easier to understand and easier to work with. So let's take a look here. They want to know how much will a change in R2 affect the overall circuit resistance, or in other words, how R2 affects this R total right here. So we can translate this into this new one. They want to know the change of R total, the total resistance, with respect to, of course, in this case, it has to be R2 because that's what we are interested in. Alright, in the end, they just want to know how much R total is going to change when R2 changes. Alright, now I am going to translate this one a little bit further in order to get this mathematical terms, and so that we know what to calculate in this example. Alright, translate this further into this change of R total, dR total, with respect to change of R2, dR2. Alright, so there you go. We have this first order partial derivative of R total with respect to R2, and that's what we need to find in this example. dr total by dr2. And as you know, when it comes to finding derivative, we have to perform differentiation. And when you perform differentiation, you have to perform it on a function or an equation. But right now, we don't have anything to work on. We don't have any function or equation right here in this example. So the next thing we are going to have to do is to find that by using the relation between this R total and R2. So next thing we need to find is the relation between this R total and R2. Make a note right here. We need to find relation between R total, excuse me, R total and R2. Alright, so we need this relation to form an equation or a function. And for this one right here, I am going to rely on the formula that we learned from maybe a long time ago, maybe in high school. In high school, we learned that if we have a circuit with resistors connected in parallel like this, we can use this formula to find the total resistance. And this formula is this one, 1 over R total equal to 1 over R1 plus 1 over R2 plus 1 over R3. If you have more resistors in parallel to this circuit, you can add them to this formula in this manner, in the reciprocal form. So let's build this box around this formula, because this is the main one that shows the relation between R total and R2. So we want this relation between R total and R2. As you can see here, when you have R total at the denominator of a fraction, it's kind of hard to perform this differentiation on this equation. So let's try to change the form of this so that we can have this R total on the upper side of this equation. So let's find out if we can have this R total on the upper side of this equation so that we can express this R total as the function of 3 variables, R1, R2, and R3. If we can have this form, then performing the differentiation would be much easier. Alright, so I'm going to try to work on the formula that I had before up here, whether I can flip things around so that I can move R total to the upper side. Alright, I'm going to work on the terms on the right hand side of this equation. Alright, now I'm going to work on this, and I get this R2, R3 plus R1, R3 plus R1, R2, and all of them divided by this common denominator of R1, R2, and R3. If you split this fraction into separate terms, you are going to get the same thing as we had on the left hand side. Alright, this term right here that we see right here is equal to this 1 over R total. And our goal right here is to flip this R total to the upper side, which means that we can flip this fraction that we have right here in order to get that. I am going to flip this. Alright, and here I am going to get this R1, R2, R3 divided by these whole terms, lots of terms right here. Alright, R2, R3 plus R1, R3 plus R1, R2. So there you go. Right now we have this R total as a function of R1, R2, R3, and it's going to be easier to perform the differentiation on this kind of form. Alright, let's make a box around that. Here we have this R total as a function form instead of just a formula. Okay, and the main form is this function of 3 inputs, R1, R2, R3. Alright, the first thing I'm going to do with this function form right here is to find the total resistance of this example. So they give us this information right here, R1 equal to 30, R2 equal to 45, and R3 equal to 90. I am going to use them to find the total resistance. And we can find that by using this function right here. We have this R1 equal to 30, R2 equal to 45, and R3 right here equal to 90. Alright, and all we need to do is to plug all these numbers into this formula. And as you know, we know this R1, R2, R3, we know all of them. Also here we know all of them right here, so we just need to plug all these numbers in and need to rely on a calculator or a computational program. Alright, I am not going to repeat the whole terms again, so let's assume that we plug all these numbers into a calculator, and in the end we get this 15 ohm out of that. 15 ohm as the total resistance. Total resistance. Alright, but this is not what they ask for. They ask for this dr total with respect to dr2. So just keep this in mind that we have this 15 ohm ready to be used. And let's move further to find this first order partial derivative. And let's work right here. It turns out that we can do this in 2 separate ways. So let's start with this method number 1. Method 1. We want to find this partial derivative of R total with respect to R2. And in this case, we are going to find it explicitly. So the keyword is this, explicitly. What does that mean? It means that we are going to work with a function. Make a note right here, function, use function. Use function form. Alright. So let's bring the function form right here. So here we have this R total equal to, right, from up here we get this R1, R2, R3 divided by all these terms, R2, R3 plus R1, R3 plus R1, R2. Alright, we have this fraction for the R total. And then we are going to perform the differentiation of this whole term with respect to R2, because we need to find this, right? So we are going to diff this. with respect to R2. Diff with respect to R2. So let's take a look at the locations of R2 in this fraction. As we can see here, we have R2 at the numerator of this fraction. We also have R2 at the denominator of this fraction, which means that we are looking at two terms with R2 inside. One at the top right here, first term with R2 inside, and we also have this term with R2 inside, so we are looking at U right here and V right here. Alright, and since we have this division between U and V and we want to diff them, we need to apply the quotient rule. So dr total with respect to R2 is going to be equal to quotient rule right here, V du, so we have to bring the whole term, the denominator term up here. V, that's going to be R2, R3. R1, R3 plus R1, R2, right? That's V, and du. We need to diff this. Du right here with respect to 2. And of course, we need to treat R1 and R3 as constants. And you diff that, R2 goes away. We have this R1 and R3 left. R1 and R3 left. And here minus u dv. Alright, u is going to be R1, R2, and R3. Now I need to diff the denominator term right here with respect to R2 and treat R1 and R3 as constants. So I need to diff this first term with respect to R2. R2 goes away, I have this R3 left. Alright, now I need to diff this with respect to R2. This is a constant, so it's going to go to 0. Now I need to diff this with respect to R2, and R2 goes away, I have this R1. So this is going to be equal to plus R1. Alright, and then we have this division with V squared. Alright, these whole terms right here, R2, R3 plus R1, R3 plus R1, R2, alright, square. So there you go. You have this expression to find this first order partial derivative, the one that we want right here. So we can just plug these numbers in. R1 equal to 30, R2 equal to 45, right? They give this to us, right? So R3 equal to 90, and we can just put them into these places. I know it's a lot, but that's the way it is. You have to plug them in order to find the final answer. And if you plug them in correctly and you use the calculator, this should come out to be equal to 1 over 9. This should come out to be this 1 over 9 right here, equal to 1 over 9. Okay, that is the final answer for this example. But it turns out that we have another way to find the answer for this example. So let's take a look at this method 2. Method 2. Alright, method 2, we are going to find this same value, dr total by dr2, but we are going to find it implicitly. Alright, implicitly. How is that going to work? We are going to use the formula instead. Use the formula, which is going to be this one instead of the function form. So let's try that out. So we have this 1 over r total. 1 over r total. Oh, let me use this blue color. 1 over r total equal to 1 over r1 plus 1 over r2 plus 1 over r3. Okay, now we have this equation and we are going to perform the implicit differentiation to this formula, to this equation. Alright, so first of all, I need more space, so let me fix this one. So we have this formula right here in terms of an equation. Alright, 1 over r1 plus 1 over r2 and plus 1 over r3 And we are going to perform the partial differentiation implicitly to both sides of the equation. We have done this before. I know you can do this. You can diff this with respect to R2. Of course, we want to know this change with respect to R2, and we are going to do the same on the right hand side of this equation. Alright, diff this with respect to R2. Okay, so let's put some space right here. Now on the left hand side of this equation, this 1 over R total is actually this equal to R total to the power of minus 1, right? This is equal to each other. So we are going to diff this with respect to R2, but keep in mind that R total is a function of R2 and R3. We have R2 inside R total. Okay, so keep in mind that R total right here is a function of R1, R2, R3, which means that we need to apply the chain rule every time we diff this R total. Alright, so let's start by differentiating this by using the power rule. Power is going to come down to minus 1, and then we have this R total to the power of minus 2. Alright, and then we need to apply the chain rule because there is R2 inside this R total. Diff, that we use this black right here from chain, diff R total with respect to R2. Alright, now that is the left hand side of the equation. Let's work on the right hand side of the equation. So here we are supposed to diff this first term with respect to R2, and as you can see here, we are working with R2. We are going to treat R1 and R3 as constants. You diff this, it goes to 0. Alright, and then you can diff this, and this term is equal to R2 to the power of minus 1. And I am going to diff this with respect to R2, and I get this minus 1 comes down, and then I have this R2 to the power of minus 2. Okay, and then I need to diff this with respect to R2. We are working with R2 here, and R3 and R1 has to be is a constant, so you diff this, it goes to 0. So in the end you have this, and I can just cancel this out, this minus 1 and minus 1. So in the end I can just find this dr total by dr2 equal to, I am going to flip this R2 down to here, R2 to the power of 2, alright, and then I am going to move this R total terms to the other side, and it's going to be equal to R total to the power of 2, and also equal to R total divided by R2 with the power of 2 outside. Alright, I know that R total is equal to 15 ohm, so I can use that. This is going to be equal to 15 divided by R2, it's given to us 45, let's use that, to the power of 2, and this is equal to, alright, 1 over 3. Alright, 1 over 3 squared, it's going to be equal to 1 over 9. Alright, as the final answer, and as you can see, it's the same as the method 1. Method 1 requires a lot of calculations. Look at all these terms right here. All of these terms. But if you work on this method 2 implicitly, you can arrive to this 1 over 9. I think it's easier to follow this method 2. Now let's move to example number 3, where we also have a problem related to an engineering applications. Alright, so let's take a look at the informations that we have right here. Here we are looking at a design of a cylindrical can. So we are working with a cylinder here. And this cylinder is supposed to have a radius of 3 centimeters and the height of 10 centimeters. Alright, so why don't we draw this cylinder right here? On this slide, we are looking at a can with a radius of 3 centimeters. 3 centimeter and the height of 10 centimeters. Right, we want this design. Okay, height of 10 centimeters. But it turns out that after producing this can, there are errors going on. As you can see here, it says that the radius and the height are off. So when they say off right here, it means that they are not the same as the design. We are talking about errors going on, and by these following amounts, the errors for the radius is 0.03 centimeter, and the error for the height is minus 0.1. And why don't we make a note right here that we have errors going on. So we have errors for the height, for the radius first. Error for radius equal to 0.03 centimeter. All right, actually what we see right here has plus going on at the front. So here it has plus right here, which means that the radius is larger than it's supposed to be. It's supposed to be 3 centimeter, but since we have this error of plus 0.03, it means that when you have the final product, it turns out to be 3.03 centimeter. So make a note right here, this is larger than the design. Okay, now error for the height as well, error for height, and here we have this minus 0.1, 0.1 with the minus sign at the front. Minus sign means that it's smaller than the design, which means that in this case the height of this can is shorter than the design of 10 centimeters. So here you can make a note right here that this is shorter than the design. Alright, instead of 10, maybe you have this 9.9 centimeter here. Okay, now we have all these errors going on, and in the end they ask us to estimate the resulting absolute change in the volume. They want to know the change delta in volume, delta V. They want to know what's going to happen to this volume when we have these errors going on, right? According to these errors, and they want to know this, all right? Why don't we start by looking at the volume of this design first? So we have this volume of this can according to the design, and we are going to use this area of the base, pi r squared, right, times the height. This is a formula that most of you know, the volume of a cylinder. And this is going to be equal to pi, and r is supposed to be 3 right here, centimeter. This is based on the design, so make a note right here, this is the design. So here we are going to have this 3 squared times the height, which is 10. And in the end, we have this 90 pi cubic centimeters. All right. So at this point, I want you to notice something, that right here, volume changes according to the value of the r and h, changing according to the radius and the height, which means that volume right here is a function of two inputs, radius and height. So we are looking at a function of two inputs, r and h, and v takes the function value. All right. So in the end, we are supposed to find this delta v, how this v changes. Why don't we try to find the change of v according to each of these inputs, all right, separately. First, try to find the change of v with respect to r, and then try to find that with respect to h later. Okay, why don't we start with change of v with respect to r. And as you can see here, this is a partial derivative of v with respect to r. And we can find that, of course, because we know how to perform the partial diff. So this is going to be equal to, oh, by the way, since we are working with r right here, I am going to make a note again that h right here is going to get considered as constant. All right, h right here going to be constant. So let's diff this with respect to r only. So as you can see here, we only need to differentiate r squared, and what we get right here is 2 pi rh, and that is the change of v with respect to r. And we can do the same for the change of v with respect to the height. Okay, and here we need to diff this same function again, pi r square h with respect to h this time, and we treat r as constant. Okay, here I diff that with respect to h, so I get pi r square. Okay, the next thing I'm going to do now is to move this dr to the other side of the equation, and same with dh to the other side of the equation. Now let's take a look what we have right here. Here we are going to get delta v dv right here. dv equal to 2 pi r h dr. Okay, and for this one we are going to get this dv equal to pi r square dh, and make a note right here, this is the change of v due to this variable r, due to r. And this one, change of v due to h. Alright, and now we want to find the total change according to both of them. So delta v that we want to find is going to be equal to the change of v with respect to r due to r, due to r. Alright, plus another delta v, plus another delta v due to h, due to the height. Alright, so we can combine these two delta v into this one equation. So we have this 2 pi rh dr plus pi r square dh. Okay, now we are going to use all the values that we have in the example into this and put them into this expression. We know r, and it's going to be equal to 3. Alright, r equal to 3, height equal to 10, dr equal to 0.03, dh equal to minus 0.1. Put them all into this expression right here, and it's going to be equal to 2 pi, r is going to be 3, h is 10 centimeter, and this dr right here, we also have the value for that, and that is 0.03, 0.03 plus pi r square. Okay, pi r square, r is 3 square, dh, and dh right here is equal to minus 0.1, minus 0.1. So in the end right here we have this 1.8 pi minus, okay, let me check. Okay, 2, 3, 3. Okay, 1.8 pi minus 9 right here. So it's going to be minus 0.9 pi. So in the end we have this, okay, 0.9 pi cubic centimeter as the final answer. Okay, and keep in mind that we have this plus right here. The delta V is plus, means that the change of the volume is going to increase by 0.9 pi cubic centimeter. So let's make a note right here, increase by this amount, and that is the estimate, increase. Okay, so that is how you use the partial derivative with the geometry of a cylinder. Now let's move to example number 4, and this is about tangent plane. Okay, alright, so we want to find the tangent plane, so we want to find a plane in 3D and that plane has to go through this point 113, and it has to be tangent to this function. Alright, tangent plane to this function. Let's take a look at this function right here, and keep in mind that we are looking at a surface. Okay, surface in 3D, and it's represented by this blue surface right here. And what we need to do right here is to find the tangent plane, which is going to be barely touching the point 113 right here on this plane, and it's going to be tangent to this surface. Alright, now first of all, let's talk about the general form of a plane in 3D. So general form. of a plane in 3D passing a certain point, passing point P0 with this coordinates x0, y0, and z0. And this is going to be point P0 for us. Now, with this general form, you are going to see this. And it's going to have this form, 0, n1, x1, x minus x0. Right here, x minus x0. And plus n2, y minus y0. Plus n3, z minus z0. Okay, and the whole equation has to be equal to 0. This is the general form for a plane passing through a certain point P0. It has to be in this form. And the question is, what is n1, n2, and n3? You can make a note here that n1, n2, and n3 are components for normal vector. For normal vector to plane. So we are talking about, well, maybe something like this. A normal vector, n right here. Alright, and we have these components of them, and we can put them into this general form to find this equation. Alright, but let's play around with this general form and make it a little bit easier to work with. So the first thing I'm going to do with this form is to divide all of them with respect to n3. Okay, start with this, divide all the equation with n3 throughout. So it's going to be n1 divided by n3, x1 minus x minus x0, x minus x0, and plus n2 divided by n3, y minus y0. Okay, and last one, n3 divided by n3, it's going to go to 1, right? So in the end I have this z minus z0, okay, equal to 0. This is what I have at this moment. And then I am going to keep this z alone on one side, on the left hand side of this equation, and the rest is going to get moved to the right hand side. So this terms is going to get moved to the other side, this one as well, and this one as well. So in the end, I am going to get this z equal to minus n1 over n3. Alright, x minus x0, minus n2 over n3, y minus y0. And then I move this minus z0 to the other side. This becomes plus z0. Okay, and then the next thing I'm going to do is to call this one a. Right? I group them together and call it a. Same with this, call it b. So in the end, I have this form for this plane. Z equal to a x minus x0 plus b y minus y0 plus z0. Okay, at this point I am going to put this p0 into this equation. So I am going to put p0 of 1, 1, 3. So let's put it in and we get this. Z equal to a x minus x0 right here is 1 plus b y minus y0 here is also 1 plus z0 equal to 3. Alright, so right now we are looking at a function of two variables, two inputs. This, make a note right here, we are looking at a function of x and y as inputs, and z takes the value of the function. Okay? Now, the next thing I'm going to do is to perform the partial differentiation with respect to x and y. So next thing, I am going to find the partial derivative of z with respect to x. So I am going to diff this expression right here, I am sorry. I'm going to diff the expression right here with respect to x. And as you can see here, I can just diff this with respect to x, and I get a right here, constant, doesn't change, and I get 1. If I diff this with respect to x, I get 0 because I treat y as a constant. I diff this with respect to x, I get 0 because 3 is a constant. So in the end, I know that dz by dx is going to be equal to what? A. And dz by dx, I can find that by working with this. dz by dx, I diff this with respect to x. Of course, I can just diff this one. With respect to x, I get 4x. Okay, here I get 4x. If I diff this with respect to x, I get 0. So in the end, it's just this 4x. And with this, I can apply this point P0, 1, 1, 3, which means that x is equal to 1. So in the end, I get a conclusion that a is going to be equal to 4. Because x is equal to 1 right here, goes into here. Alright, a is equal to 4. Now let's find out about this b. And we can find that by performing partial derivative of z with respect to y. Alright, I'm going to need to diff this with respect to y. With this one, there is no y in there, and x is treated as constant, so it's going to go to 0. For this one, next one right here, I need to diff this with respect to y. B at the front is constant, so I keep it the way it was. Then I diff the inside, I get 1. Which means that dz by dy equal to b. And after that, I am going to find this dz by dy right here from this surface that they give to us. I am going to diff this with respect to y. Diff this one with respect to y, it goes to 0. Diff this one with respect to y, I get 2y. So in the end, I have this b equal to 2y. And once again, I can apply the point that I have, 1, 1, 3, which means that y equal to 1 and goes to here. And it means that I have this b equal to what? 2. Alright, this looks good. Now I can move back to this equation right here. This equation that I had earlier right here. Now I know the value of a and b, so I can just plug them in to get the complete equation for the plane. Now let's put it right here. So this is going to be z equal to a is equal to 4. So 4x minus 1 plus b right here equal to 2, y minus 1, alright, and plus 3. And that is it for the tangent plane to the surface at the point 1, 1, 3. So what you are looking at here is an equation for tangent plane to this function that they give to us, z equal to 2x squared plus y squared at this certain point at 1, 1, 3. Okay, there is one thing that I want you to remember is that when it comes to this tangent plane, we can use it to approximate. We can use this to approximate. Can use to approximate function value around this certain point. Right, this certain point, in this case, it's 1, 1, 3. We call this kind of approximation linearization. So let's make a note right here. This is linearization. Alright. And keep in mind that it has to be around, it has to be close to this point. You can't go far. If you go far, then the arrow is going to be big. So this is the idea of linearization. Use the tangent plane to approximate the function value. Now let's apply this idea to example number 5 right here. In this example, we are supposed to find the linearization of this function right here. Linearization of this function. As you can see, we have this formula for this function to be used. Okay, and we are supposed to find the linearization of this at this point, 1, 0. So what you are looking at right here is a reference point, x0 and y0. And after we found the linearization, we are supposed to use that to estimate the function value at this point, 1.1 and minus 0.1. As you can see here, this point is quite close to that point, that reference point. Alright, so our job is to find this approximation. Reading up to here, some of you might ask me, why do we need to estimate at all? Because we have the formula for the function available right here. We have this one right here. And if we want to find the function value at this point, 1.1 and minus 0.1, why don't we just plug these numbers into this formula and get the function value out of that? Well, yes, we can. Let's do that. So, if you want the function value of this, okay, at this point, 1.1 and minus 0.1, just put these numbers into this formula. And of course, we get this function at 1.1 and minus 0.1. And it's going to be equal to x equal to 1.1 times exponential of x times y. Here we are going to have minus 0.11. And if you put this into a calculator, it's going to come out to be 0.9854. So yes, you can. You can just plug these numbers into this formula and get the function value out of that. But the thing is, sometimes in some applications, you are not going to get this. Sometimes this may not be available. Alright, and in those times, you are going to rely on the linearization right here as the only option you have. So in this example, we just learned how to use the linearization and the concept of it. So just keep that in mind. Sometimes this might not be available. Okay, so let's try to use what we learned from the previous example to here. In the previous example, I told you that we can use the tangent line to approximate the function value near a certain point. So let's move to example 4 right here. So let's bring this formula that we have right here to this example number 5. So it's going to be the equation for the plane, tangent plane in the 3D space. And it's going to be this. I have this before. Z equal to a x minus x0. Right? I bring the whole thing here. Plus b y minus y0 and plus z0. And I told you that we can use this to approximate. To approx f of x, y. Alright? Now, the first thing I'm going to do here is to modify this equation into a formula that is nicer to use. So the first thing I'm going to do here is on the left-hand side of this equation, I am going to change this z into an approximate of this function of xy, and I'm going to use this sign instead. Approximation is going to be linearization. Linearization L at x and y. Okay, and now let's do something on the right-hand side of this equation. I am going to take a look at this one first. First of all, I know that in this case, in the previous example, z is a function of x and y, right? And we can add 0 to here. We can add 0 to this x and 0 to this y, and it turns out that we are going to get this z0. So I am going to substitute this with f of x0 and y0, and I'm going to move it to the front. z0 becomes f of x0 and y0. In other words, this is the function value at the reference point. So make a note right here, this is reference point, ref point. Okay, now let's take a look at the next term. Let's take a look at this term right here, a. in the previous example, we found a to be equal to z with respect to x, partial diff of z with respect to x, and since z right here is equal to the function value, I can change that z right here to function value at with respect to x. So here I am going to get this f with respect to x, and just like before, I evaluate this df by dx at the reference point. So this is going to be evaluated at x0 and y0. Alright, let's move to here. We did that right here. We evaluate this dz by dx at the reference point, and we are going to do the same here. Now let's keep the back term right here the same, x0, x minus x0. Okay, plus, and we have b right here. And in previous example, we have this b equal to the partial diff of z with respect to y. And since z right here is the function value, this is going to be f with respect to y. So we can use that right here. Partial diff of f with respect to y, and we are going to evaluate this at x0 and y0, same reference point. And we did the same thing right here. Okay? Now, back to here, last term that we have is this y minus y0. So let's bring it to here, y minus y0. And there you go, you have this formula for the linearization. Okay. All these terms, if you find all of them, you can use it to approximate function value at x and y, and make a note right here. When x and y are near x0 and y0, it has to be near the reference point. Okay, so that's all you need for the linearization. As long as you have this formula in your hand, everything else should be easy. Alright, now let's try to use this on this example. First of all, let me erase this because I am going to need that. It turns out that this time we have this formula available, so let's use them. Okay, so as you can see here, we are going to need this fx, f with respect to x, and f with respect to y, so let's find that. So first of all, let's find this f with respect to x. So we are supposed to diff this with respect to x, and as you can see here, we are looking at a product of two terms with x in it. Front term and the back term, both of them has x in it, so we are supposed to apply the product rule to this. Fx right here is going to be u dv. U is x, dv, I diff this e to the power of x and y with respect to x. I am going to get this same exponential x and y, and then I apply the chain rule and diff the power up here with respect to x. I get y out of that. Okay, so there you go. I have this y right here. Alright, plus v du. V right here is e to the power of x, y, and diff u right here. U right here with respect to x, I get 1. Okay, so I get this fx. Since this doesn't matter right here, I'm going to erase it. Now, what about f with respect to y? I need to diff this with respect to y, this same function, and as you can see here, there is just one location for y up here. So it's going to be easy this time. I keep the constant at the front right here, and I diff this exponential with respect to y, and it stays the same, and then I perform the chain rule. To diff the power up here with respect to y, I get another x. That's why I have this square right here. Okay, so this is fx and fy. So the next thing, let's find these values at x0 and y0. x0 and y0. x0 and y0, which we already know it's 1, 0. Okay. Alright, it's going to be 1, 0 and 1, 0. So let's plug these numbers in, and we are going to get this fx at 1, 0 is going to be equal to, okay, alright, so 0 goes in here, it's going to go to 0, and 1 and 0, so we are going to have this e to the power of 0, and it's going to be equal to 1. Alright, now let's try on these terms. We are going to put 1 into here, and 1 and 0 to here, so in the end we have this e to the power of 0 again. So f with respect to y, 1, 0. Plug all these numbers in. I have this 1 e to the power of 1 times 0. So in the end I have this 1. Okay, well, why don't I work on this more for you to make it more clear. So I have this x equal to 1, e to the power of 1 times 0, right, times y, plus e to the power of 1 times 0. This term goes to 0, and this term I have 1. So two of them I have 1. So I have found this equal to 1. I have found this to be equal to 1. What about function value at x0 and y0? I need to find that. So function value at x0 and y0 is going to be equal to, let's use this formula. It's going to be equal to x right here. It's going to be, oh, by the way, x0 times exponential of x0 and y0. And we are looking at 1 and 0 here. So as you can see, we are going to get this 1 right here and 1 right here and 0 right here. So in the end, we have this 1 for the function value at x0 and y0. Okay? Now, let's put everything into this formula. The linearization, right? L of x and y. Okay, it's going to be equal to the first term right here. Function value at x0, y0 at the reference point is equal to 1. Plus partial diff of f with respect to x at the reference point, and it's equal to 1. Again, and with this, x minus x0. So we have this x minus x0. x0 equal to 1. Okay, the reference point, plus fy. Once again, fy equal to 1, so I don't need to put anything here. And we have this y minus y0. y0 is 0. Okay, so in the end, what do we have here? We have this equal to, right? 1 right here, cancel with minus 1 right here. And in the end, we have this linearization of this function at this point to be equal to x plus y. All right? Once again, this is linearization at x0. So I should say that 1 and 0. At point 1 and 0. And you can use this to approximate function value. And for this function value, this is equal to x to the power, x times exponential to the power of x and y. So here we have this approximation right here, and this is the true value. Make a note, true value. And this is approximation. Okay, so you can choose which one you want. This one is going to be exact and accurate, but this one, x plus y, let's try to find that. Linearization. Linearization at, they want to find the linearization at 1.1 and minus 0.1. So this is going to be equal to x plus y. So x, 1 plus 1 plus y, which is minus 0.1. And it comes out to be just 1 right here. So the approximation is equal to 1, while the actual value is this, 0.9854. So true value is right here. We use the function formula. Alright, and this one is approximation. Okay, so you might ask me, why do we need to use approximation when we have an error? The thing is, as you can see here, approximation that we have right here is so simple to calculate compared to this x times exponential x to the y, sometimes you might not have a calculator. So you might choose the approximation to be good enough. So that's up to you. So what you see right here, simpler calculation. But this one is more accurate. I should say accurate. This one is accurate. This one simpler calculation, but with small error. Okay? Alright, so that's the idea how to use linearization to approximate a function value at a certain point.